Hello friends, welcome to Mu Lessons. Today we meet here again with a new one, that is studying about the magnetic properties of different types of magnets and metals. So for the first time we are studying this, so we will start with the basic concepts. That is, the magnetic force appears whenever there is moving charges. Whenever a charge moves from one place to another, magnetic force appears around it. So these forces are represented by these imaginary lines. You can see these are the magnetic field lines. You can recall what you have read in the right hand thumb rule. Whenever the thumb points to the current side, direction of current, and the curl of the other fingers shows the magnetic field. So you can apply that rule in this case also, and you can find the direction of magnetic field by the curl of your fingers. So for this part you need to just understand, whenever the charge moves, it creates a magnetic force around it, which is shown here by these dotted lines and these circular lines. These are the continuous lines starting from north and ending at south. These are called the magnetic lines of forces, and they are around a current loop or a bar magnet you can find. Now what is a magnetic dipole? The magnetic moment is represented by this vector. Dipoles means having two poles, that is a north pole and south pole. That a bar magnet, when having two poles, denotes the magnetic dipole, two different types of poles. Now coming to the magnetic field vectors, we have two types of field vectors, that is the magnetic field strength and the magnetic flux density. Magnetic field strength is given by H, denoted as H, and magnetic flux density is denoted as B. So you can see a solenoid type structure in which the current is flowing and there appears a magnetic strength around it, and that magnetic flux density is given by B, which is equals to B0 equals to mu0 into H. This mu0 is the permeability. Permeability means the extent to which the magnetic lines of force can cross the body, or the extent to which the magnetic lines can link to a particular body, that is given by the permeability, or the strength of linking of magnetic field lines to a body. So there is a relation between magnetic flux density and magnetic field strength, that is B0 equals to mu0 into H. Now whenever a current, you can see a core of iron core is entered into this solenoidal structure. So this B value, that is the magnetic flux density, changes to B is equals to mu into H, and in this case this mu is the permeability of the material used as a core in this case. So it becomes B is equals to mu into H. So in this case what happens, mu0 changes to mu, or you can say the amount of linking of magnetic lines of forces to this material also increases, and this will be more effective than the previous one. Now mu r is given as the relative permeability, which is equals to mu by the absolute permeability, that is mu0. Now on the part of magnetization, we can have B is equals to mu0 into H plus mu0 into M, and M is given as xi m into H. This is denoted as psi, that is the magnetic susceptibility, and it has a different formula, that is relative permeability minus 1, that is the maximum susceptibility, magnetic susceptibility. Now for finding B, you need to find the value of field strength, that is H, and this field strength depends upon the components used here, that is the length, the current flowing through the conductor, and the number of turns. So magnetic field strength is given as H equals to N into I by L. Now how these magnetic moments, there is an origin of magnetic moments, we will discuss on this. On the response to the quantum mechanics law, there are two main contributors, that is the orbiting electron, that is an electron moving around it, and then the spin of the electron itself. There is a spin of electron, two, that is plus half and minus half, we have seen in class 12. So these two are the main contributors for the origin of magnetic moments. Whenever the electron rotates around it, a positive part, that is a nucleus is the positive, remains as the positive, and electron is the negative part, having the constant diameter radius, it moves along a circular path, so it creates a magnetic field, and this is the direction of magnetic moment. Similar to the case of the spin of the electron, the spin is an intrinsic property of the electron and it is not due to its rotation. You should remember this one. Now these all things, that is the magnetic moments, are measured by a particular unit, that is a Bose magneton, and the Bose magneton is given as plus or minus 9.27 10 to the minus 24 ampere meter square. Its unit is current into meter square, that is ampere meter square. Now discussing about the magnetic properties, we will discuss about the magnetic materials. How many types of materials are there? You have come across these terms: diamagnetic materials, paramagnetic, ferromagnetic. So in case of diamagnetic materials, in the presence of field, dipoles are induced and align opposite to the field direction. So this is the basic characteristics of diamagnetic materials. In this case, the magnetic field strength is 0, that is H equals to 0, because there are no H found in this case. You can see in the diagram, no dipoles are found. And whenever in the presence of field, these dipoles are induced and they align to the opposite to the direction of the field direction. That is, in this case, whenever it is applied electric field around them, the field direction is given by H and the induced aligned directions is opposite to the direction of H. Similarly, we have another, that is the paramagnetic materials. In this case, the paramagnetic materials are found by the unpaired electrons. In case of diamagnetic, we don't have any unpaired electrons, so it is vacant. In case of paramagnetic materials, we have the unpaired electrons, and whenever it is kept in the presence of field, they align themselves in the same direction of the field. So this is the basic difference between the diamagnetics and paramagnetics materials. Now previously we have seen how B varies with inserting a magnetic core, or you can say an iron core. The relative permeability changes. The flux density B versus the magnetic field strength H for diamagnetic and paramagnetic materials is shown in this case. And the diamagnetic slope is little bit lesser than the paramagnetic slope. This is the BH curve. And this is just for information you need not need to mug it up. These informations are already in your book. These are some values of susceptibility of diamagnetic and paramagnetic materials. Now coming to the next, that is the ferromagnetism. There is a mutual alignment of the atomic dipoles even in the absence of an external magnetic field. Even this is the main point to think, that is, even in the absence of an electromagnetic field, there is an alignment of the atomic dipoles in this case also. That is, so it is known as the ferromagnetic materials. It is due to the coupling forces allowing the magnetic spins. In this case, we have the formula B is equals to mu 0 H plus mu 0 into M, and in this case the value of H is nearly equals to 0, so we can eliminate this. So magnetic flux density is equals to directly proportional to, or you can say it is equals to mu 0 into M. Now this magnetic flux density will grow to a saturation magnetization, that is MS, which is saturation flux, and then it will stop. Several values are given below, you can see, but you need not need to remember all those things. Now another type, that is the antiferromagnetism. In this case, antiparallel alignment of spin magnetic moments for the antiferromagnetism diodes. Like the example is magnesium oxide. In this case, there is an antiparallel alignment of the spins of the magnetic poles. You can see these are anti-parallel directions. They have arranged themselves in such a way. But at a very low temperature, that is at low temperature, that is the temperature is known as the Néel temperature, they all become paramagnetic. That means they will align to the same direction of H. Now there is ferrimagnetism, spin magnetic moment configurations for Fe2 plus and Fe3 plus in Fe3O4 ferrous oxide. You can see in case of ferromagnetism, all the dipoles, all the moments are aligned in the same direction. In case of ferrimagnetism, most of them align the same direction, but some are anti-parallel to them. And in case of antiferromagnetism, the same number of moments are opposite. Means if n number are in same direction or parallel, then same n numbers will be in the anti-parallel direction. So this ferromagnetism requires free electrons in the conduction band, but ferri and antiferro can occur in the insulators also. So this is the main important part to think, that is the ferri and antiferromagnetism can also occur in the insulators because they don't require any free electrons in the conduction band. And there we can find these types of magnetic materials in case of metals and metal oxides. But if you consider the ferromagnetism, we have to take the metals where we can find the free electrons in the conduction band. Now all these cases happen below a particular temperature, that is known as the Curie's temperature. Below the Curie's temperature, these materials behave in their own form, that is the ferromagnetic, ferrimagnetic or antiferromagnetic. And whenever this temperature exceeds the Curie temperature, above this Curie temperature it becomes paramagnetic, that is they will align in the same direction of H, magnetic field strength. So these configurations are formed only below the Curie's temperature, and above it becomes paramagnetic. Similarly, in this case it is a little bit elaboration of the previous one, how the alignments or the configurations takes place in case of Fe2 plus and Fe3 plus. Now the important thing is the BH curve, that is the flux density to the flux magnetic field strength curve. This is very important. In case of ferromagnetic or ferrimagnetic material, there is initially unmagnetized, and there is domain configurations during the several stages of magnetization. This graph shows you how it changes from origin till the saturation point. At saturation flux density, that is BS, magnetization MS, initially permeability mu I. In this case all the values are given. You can see how the value of H changes as it reaches from origin to the saturation value. Now the magnetic flux density versus the magnetic field strength gives you the hysteresis curve. This is the very popular thing, you have heard about it. The ferromagnetic material are subjected to forward and reverse saturation and the hysteresis loop, that is a red color loop, but initial magnetization is given by this blue color line. The loop is first formed from S to S dash, and after that there takes a field removal, and hence the loop again converts into the, means it again acts in the reverse direction, and we get this hysteresis loop. So summing up today's video, we have seen some points like a magnetic field can be produced by putting a current through a coil, or magnetic inductions occur when material is subjected to magnetic field or there is a change in magnetic moment from electrons. We have seen some types of magnetic materials like ferri or ferromagnetic material which have large magnetic inductions. Paramagnetic have very poor magnetic inductions, and diamagnetic have opposing magnetic moment, or you can say no such magnetic moment exists in case of diamagnetic, very less. Hard magnets have large coercivity and soft magnets have very small coercivity. This term coercivity you can find from book. These are on the basis of the BH curve. If you will read in detail the working, how the BH curve is formed, you will understand everything. So there are some examples of magnetic storage media like iron oxide in polymercuric film, keeping safe the tapes and floppies, a thin film of COPTCR, that is cobalt platinum chromium, the glass disk or the hard drives. So this was about magnetic materials, types of magnetic materials. We have not gone in detail regarding this, so we will see in our next video. Thank you.